Good. Let's start with the equations that we looked at in this class. And basically it's a 1D, the 1D equations. So what would be the heat equation? Who remembers that one? The full equation for temperature.
It's derivative of the temperature with respect to time.
Right. So let's start with density.
Yes, density.
Rho. Then the heat equation has what kind of parameter? Material parameter?
The conductivity?
Conductivity.
The specific heat in this case.
The CV.
Right.
CV, yes.
So we usually use this CV for specific heat. And then we have something with the temperature field, the time dependence of it. So is it first order, second order derivative?
First order.
First order derivative.
First order.
Time, T.
Yes.
And then let's put the other parts on the right-hand side.
Yes.
So the temporal behavior is equal to what? Now comes the complicated part.
The first derivative of the kappa time, the first derivative of x.
The derivative with respect to x.
Right, the general form uses the derivative with x. Then kappa is what?
Conductivity.
Conductivity, exactly. And then comes again this derivative with the temperature field, right? And if we want to include a source, we just add a source term. So heat sink or a heat source, whatsoever. Good.
Professor?
So, yeah?
I have a question here.
Mm-hmm.
I'm wondering, when we say that the medium is homogeneous, does it mean that the conductivity does not change via the x? And what about...
Here it is allowed to change. When we write it in this form, we use a very general expression.
Yeah, I'm wondering that if we say that our medium is homogeneous, does it mean that K will not change via the X, right?
Exactly, right.
There is
then
no...
we can say K is a constant, yes.
And there is no relationship with the density or specific heat. It means that they can change. Is that right?
Right. Usually we have, they are allowed to change for a heterogeneous material. So they become a function of position. So rho would be a function of position, so would be specific heat, so would be conductivity. That means they are allowed to change for a heterogeneous material. If the material is homogeneous, then these are just constants. So the homogeneous case, now we can actually write that down.
Okay.
So for homogeneous material, we have rho would be a constant. So would be specific heat. And so would be the conductivity. So then we can simplify the equation a bit. Especially this part here. You see the derivative here. Now, if the conductivity is constant, you can just take it in front.
Yeah. And Professor, what about the heat source? When can we say that we have no heat source?
Well, as soon as you, for example, would turn off the heating, let's say you have a little heater, you turn it off, then you just let it go. So there is no source anymore, no heat source.
Okay.
So if we write it with F, with this source term, then it would be called an inhomogeneous equation.
It means
If
the F
we,
equals 0?
let's say it again.
If the homogeneous, oh no, if there is no heat source, that means the F equals 0. But if F has a
Right.
value, then there is a heat source, right?
Right, yes.
So last time, I remember the last time then you say that if then F equals 0, then we can say that this medium is homogeneous. But what about capacity, conductivity here?
Right, so there is two things. The material can be homogeneous or inhomogeneous. And when we say the homogeneous material, then we have that the kappa, rho, CV, they are constant. They don't change with position. But we can also say the equation is homogeneous or inhomogeneous. And on top you have the inhomogeneous equation because we have this source term. If we take the source term out, which basically means we just let the system evolve from its initial state without forcing it, then it's governed by the homogeneous equation. Then this F is 0, and we call the equation then a homogeneous equation.
Okay.
So you have material, homogeneous, inhomogeneous, but also the equation can be homogeneous, inhomogeneous. But the equation doesn't mean that the material then, if the equation is homogeneous, it doesn't mean the material has to be homogeneous. They're independent of each other. So we can use the homogeneous equation with an inhomogeneous material.
Yes. Okay, I got it.
Good.
Thank you, Professor.
So for a homogeneous material, so we have these constants, and then we can actually write it in a much simpler way. We just take these factors where we have the conductivity, density, specific heat. Take it here as a factor. And then we have the second order derivative, temperature, plus F if you want. So that would be the inhomogeneous equation for a homogeneous material. And then this factor here, because it's a constant, we can just call it D. And D would be the diffusivity. And so if you see an equation in this form, then we also call this the diffusion equation. Which is a very simple equation because it has a temporal derivative, first order, and this is the main part here, the second order spatial derivative. So we stop the diffusion equation. And in this case would be for a homogeneous material. You see, sometimes people use these kind of equations also for heterogeneous material. Let's say they would use T temperature field, then diffusivity is now a function of position times this diffusive term, T exit T. And that's not quite the same as the heat equation at path. So in principle, it would be more this thing. Which would be the exact equation when you have a heterogeneous material, which you just specify by diffusivity. But then again, it's not quite the same as if you would have the heat equation, which you would have here specific heat factor, and then comes the derivative. And now the diffusivity becomes the conductivity. So there are some simplification if you go from here to here to here. But if the material is homogeneous, then this is fine. Then that's the same. So if we have homogeneous material, the equation is exact, but not if it's an inhomogeneous material. Do you see that? See the point? Good. So there would be a small correction factor that you would need to include. Good. But that's the heat equation. The other main equation was the wave equation. So let's put that down as well. The wave equation is the other equation we were focusing on in this class. Who can tell me what to write down for the wave equation?
The right part?
Say it again?
The right part? Did you mean the right part? The left part of the, or the right part of the equation?
Well, start with the left one.
Or the left. The density times with the second order derivative of the displacement with respect to the time.
And what is at the beginning, you said?
Density.
Density.
Density, rho, good. And now we have the second order time derivative. What do you want? Well,
Displacement.
Displacement, let's use U.
Yes.
Sometimes we use S.
S.
Doesn't matter, let's use U. And now the right-hand side.
Derivative with respect to this displacement or X.
Right, and then, so this term becomes very similar like in the heat equation.
The shear modulus or Bolt modulus.
Which one you prefer?
Shear modulus.
Shear modulus for elastic.
So yes, we look at the shear wave.
For the shear wave, yes.
And then comes again this derivative of, oh, now we have mu and u. Well, okay. You see, sometimes then, just to avoid confusion with mu and u, we just use S for displacement. Right? Plus F, plus the source. And so here mu would be shear modulus. And again, mu would be a function of position. Density. Which could also be a function of position. And then displacement S. Good. And obviously, you can simplify it as well for a homogeneous material. So if you would have a homogeneous material, then we have density becoming a constant. So is the shear modulus. And then we can just write it this way, like mu over rho times the second order derivative of S plus F if you want. Or in principle, it's slightly different F because we would have this 1 over rho factor. So don't really, at this point, bother about that point. Or maybe just take it out. Let's just use without the forcing term. And so what is this thing here? Shear modulus
Velocity is
divided by
square.
rho.
The
So
wave
it's the wave speed, yes, right. So often we use c, and so it will be c squared. In this case, that would also be a constant, actually. So we can write the equation as c squared times derivative of s. Good. So if you want to write down the wave equation in its most simple form, then you would have it this way. So that's the most simple way of writing down the wave equation. And this would be the heat equation or the diffusion equation. Its most simple form. Right, so now let's look at the methods we had so far. Those are the two equations we were focusing on. Now let's have the methods. And so we started with finite difference. Then we had, who remembers what was the next one we had?
Pseudospectral.
Pseudospectral, right? Then
Finite element.
finite element, right? And the most recent one, the spectral element, right? And so the main difference here between these four methods was that we used the strong form of the equation for finite difference and pseudospectral, and the weak form or the variational form for the finite element and spectral element. And then what's the main difference between finite difference and pseudospectral?
The accuracy and the use of the
High and above grid points are used in pseudospectral.
It's usually the order of the scheme that are used. Yes. So finite difference is usually low order, and the pseudospectral can be called infinite order schemes that we use. And the same we can say for finite element and spectral element. Which one would be the low order?
Finite element.
Finite element.
Element, right. Usually low order schemes. And then the spectral element would usually be a high order scheme. Right. And you saw like finite element, spectral element, pseudospectral. They're basically, right. Dealing with the spatial derivatives. But when it comes to the time schemes, the main difference that we saw in time scheme is what? You still remember what the main difference was with these time schemes? How we called that?
Explicit and implicit schemes.
Right, right. So the main characteristic was if it was an implicit or an explicit scheme. So we looked at both when we looked at the finite difference methods. We had both an implicit scheme and an explicit scheme, depending on what the choice was for the finite difference approximations. And then when it comes to these explicit schemes, what was the main point here? About the stability?
Conditionally stable.
Right, so the explicit scheme was only conditionally stable. So the stability condition is called the CFL, the Courant-Friedrich-Levy condition, which tells us how large the time step can be. If it goes beyond that, it becomes unstable, the scheme. Good. So that was basically what we looked at in this class so far. So you see strong form, weak form, low order, high order methods, implicit, explicit schemes, conditionally stable, unconditionally stable. All these kind of expressions we already saw in this class. So these are like main points when it comes to numerical schemes. And things we didn't look at yet. So that's what we had so far. The missing points or details. let's say when it comes to finite differences, finite difference methods, something we didn't touch too much was about the grids. We assumed we had just have a regular grid, and then we used schemes often which are non-staggered schemes. But especially for wave propagation, the staggered grids, grids, finite difference schemes dealing with staggered grids became much more popular, actually. We touched it a little bit when we looked at higher order finite difference schemes. But if you would solve now, for example, the wave equation, you would very likely go to a staggered grid. And when it comes to grids, there are more ways as well. We could have rotated or curvilinear. Grids, which are still using finite difference schemes, but now the gridding is a bit, is not just a regular grid anymore, but curvilinear grids, for example, they could have some stretching involved, so that we have these no more regular grids, but then a stretched grid, for example, with the height. And so curvilinear grids become popular, for example, when we would have topography, trying to map the topography with the grid. And so they go from a regular grid with no topography to a curvilinear grid. This usually involves a mapping as well. So you have a mapping function to map from the regular grid, just the same spacing, to these stretched coordinates, basically, the grid. That would be curvilinear grid. So that's something we haven't looked at. Also, what we just ignored so far are absorbing boundaries. And especially when it comes to wave propagation, there are, for example, the PML, perfectly matching layer absorbing boundaries, which became like highly efficient absorbing boundaries. But we also have, for example, a Sommerfeld condition, and we look at acoustic waves or the Clayton and Enquist absorbing boundary conditions for wave propagation. So these would be implementations of absorbing boundaries that we would also have to look at. Right, and then in terms of other methods, let's call it other methods. Probably the method we haven't looked so far, and which is the most popular other method we haven't touched yet, is the finite volume. So we have finite difference. It's pretty much the most popular scheme and method. Then finite element, but then also the finite volume methods. especially when it comes to fluid dynamics, for example, the most popular approach. And so let's look at that next time. The next one would be discontinuous Galerkin. Oh. And it pretty much goes from low order to high order as well. So they use similar ideas, but finite volume methods are usually low order, whereas discontinuous Galerkin methods are usually high order. And then a little bit more exotic ones that have been used for especially wave propagation as well are like lattice Boltzmann methods. And these lattice Boltzmann methods, they usually use a concept with masses attached to others by springs. And then you can have these mass points just in a very irregular fashion ordered. Etc., etc. So they become very irregular grids basically, and you don't really need a grid anymore. You just need these mass points, which you then connect with each other using springs. And just by this connection, you can basically propagate waves through such a grid. And they have been, they are very flexible in the way of how you start gridding, how you put these points, especially popular for volcanoes. Do you know why volcanoes are very tough problems to mesh?
They're constantly changing.
It's not that. It's more like the way how they the material changes in volcanoes. Have you ever been to a volcano? Faustino, you have been? You were walking up to a volcano, the crater?
Up to the crater, yeah, in Costa Rica, but well, you can see the lava in Nicaragua too. Yeah.
Good. Was it difficult to walk up or not?
No, it's just a tourist way. You can walk through a path that is made. It's not that so difficult.
Okay, then you had an easy volcano.
Yeah.
Often what you find with volcanoes, very typical ones, they have this very loose material. You have to walk through like loose gravel material up to the crater. This is very typical in Italy, for example. You go up to Stromboli, etc., Etna, because they throw out all these material and then you have very loose gravel on top. And it's actually quite tough to walk up there because with each step you sink down another half step. Now, if you want to model these kind of stuff, we would have like a thin layer, which is very loose material, porous material, and then only comes a more, let's say, solidified material. And that's usually difficult to mesh properly with the methods we had so far. But now with these lattice Boltzmann methods, it becomes quite straightforward of just assigning points here wherever you like. And then the spring basically tells you how loosely coupled these points are, these mass points. So just by the string stiffnesses, you can basically accommodate this loose layer at the volcano, and there's a more compact material below that. So it's a method which gives you a large flexibility in accommodating that.
Professor Daniel, we received the courses for the next year, for the next semester.
Mm-hmm.
And I thought maybe you're going to give a second course of this, of computational geophysics. It's not, I mean, you don't give this course anymore, a second course, an advanced course of this?
No, we only give this introductory course, because then advanced courses would focus probably on one particular method, one particular approach. And there is no one method that we teach at the moment, right? Yeah, computational geophysics only gives you a kind of an introduction, and then it wants you to, like, from there on, use your own wits and curiosity to dig into the specific method that you want to use for your PhD work, for example. This is more meant to be a kind of an overview on numerical methods, right? The other class I'm teaching was seismic waves. There we focus then on wave propagation topics. And it has been seismology 2 previous years. Now we split seismology 2 into a seismic wave propagation part and an earthquake source part. So earthquake source physics. The source physics part is not taught by Martin May, and I'll do the wave propagation, but we start alternating that. That was the idea.
So the wave propagation is for the second semester of next year, I guess.
No, wave propagation will come 2022.
Okay.
I was teaching it this year. So this year in spring. Now next spring will be earthquake physics.
Yes.
And then comes again wave propagation, seismic waves. That's the idea, basically, doing that.
Okay. Professor, I also have heard about the particle-based simulation, a particle-based method like discrete element method, and other method that usually used in the hydrodynamic simulations. Is this a kind of the lattice Boltzmann methods?
Right, there are yeah, these cell tracer methods as well. Yes, they are sometimes used, like for example in tectonics. If you want look at how plate tectonics would look like, subduction zones, etc., how they would evolve. You sometimes have these particle in cell techniques and methods they use, right? Sometimes used in geodynamics. Right. I don't quite know how they call it exactly, but there's like a particle in cell, something. And they use cell tracers, etc. Right. And often they are, these kind of methods are more meant for nonlinear problems, nonlinear equations. Right. Very interesting methods as well. Yes. You see it in geodynamics often, yes. Yeah, there are probably still way more than that, which I keep forgetting. But if we would look at wave propagation part, then the top, this one has become a very popular approach for wave propagation as well. Finite volume, not so much for wave propagation yet. Lattice Boltzmann, only very few groups use that approach. And all other groups basically use one of these methods. Finite different pseudospectral, finite element or spectral element. So right. Good, we have to finish. I have to see what the division is doing. Let me stop here, this one. Good, so we don't have time much for SpecFem, but try it out, try download it. Go into one of these example folders, just run the run script if you can, and you have the qubit measure. Trellis is not responding at the moment. Might be somebody is using it. But I saw they will shut down the license server over the weekend, I think. So maybe it's responding again after that. IT every now and then does some maintenance on these license servers. We'll see after that maintenance session. But again, Trellis is basically only a single user license. So if you're not using it, you would have to close it so that somebody else can use it. No, good. Let's see each other next Sunday. And then we look at like one of the most popular methods for commercial packages, the finite volume one. Good. Then I wish you, yeah?
When is the due of the homework 9? Next Thursday?
No, you don't need to make a report about that, homework 9.
Okay.
Just whenever you have time and you want to see how that would work, try it out, yes.
Okay.
No need for a report or hand in something. Good.
Thank you, Professor.
Good, so let's see each other Sunday again.
Thank you,
Then I
Professor.
wish you have a good weekend.
You too, bye.
And take care in case the rain comes. Bye, everyone.
Bye.